The second derivative test. The second derivative provides an alternative method for distinguishing between turning points, i.e. for distinguishing between a local max, local maximum, and a local min, local minimum. The curve opposite has a local max at A. So here's our curve, it's cubic, and here's A, our local max, and a local min at B. So there's our local minimum at B. The difference between the 2 points is that the local max, the curve is concave downwards, so it's N-shaped, it's concave downwards, while at the local min, the curve is concave upwards, so it's U-shaped. This gives us the so-called second derivative test for turning points. Second derivative test for turning points. Suppose x1, y1 is a stationary point. Part 1. If d squared y dx squared, so the second derivative is less than 0, at the point x1, y1, then x1, y1 is a local max. So we get a local max when the second derivative is less than 0. Part 2. If d squared y dx squared is greater than 0, so if the second derivative is greater than 0 at the point x1, y1, then x1, y1 is a local min, or a local minimum. So we get a local minimum when the second derivative is less than 0. It is important to note that the second derivative test cannot identify saddle points. If d squared y dx squared is equal to 0 at a stationary point, then the point may be local max, a local min, or a saddle point. On our course, the only way we have of being sure what type of stationary point is involved is to use the first derivative test. Find the coordinates of the local maximum and local minimum points of the curve y equals x cubed minus 3x squared minus 24x plus 10. So we start by getting the stationary points first. So basically let the slope, or dy dx, which is the same thing, equal 0. So if y equals x cubed minus 3x squared minus 24x plus 10, then dy dx equals 3x squared minus 6x minus 24. So what we do is we let this equal 0, so we put dy dx equal to 0, and then we solve for x. So we have 3x squared minus 6x minus 24 equals 0. We divide across by 3, getting x squared minus 2x minus 8. We factorise, and then we solve. So x plus 2 equals 0, so x is equal to minus 2, or x minus 4 equals 0, so x is equal to positive 4. So we take our curve, or our function y equals x cubed minus 3x squared minus 24x plus 10, and we swap each of our x values for minus 2. So if x is equal to minus 2, we have y equal to minus 2 cubed minus 3 times minus 2 squared minus 24 times minus 2 plus 10, which gives us 38. So 1 point is minus 2, comma 38. And then we do the same with 4. So we get 4 cubed minus 3 times 4 squared minus 24 times 4 plus 10. We get minus 70. So the other point is 4 minus 70. So remember, we were asked to find the coordinates of the local maximum and the local minimum. So the 2 points that we worked out in the previous slide were minus 2, 38 and 4 minus 70. So now we find the second derivative and use it to determine the nature of these stationary points. So we have our 2 stationary points. We just have to figure out which one is the local max and which is the local min. So if the first derivative, dy dx, equal to 3x squared minus 6x minus 24, then d squared y dx squared is equal to 6x minus 6. So the second derivative is equal to 6x minus 6. So we just differentiated this again. So if x is equal to minus 2, we swap that x in the second derivative for minus 2. 6 times minus 2 minus 6 is minus 18, which is less than 0. Thus, minus 238 is the local maximum point because we got the second derivative to be less than 0. So we have a local maximum point. So we would have an end shape at this point. So we'd have a local maximum. And then when x is equal to 4, we swap the x in the second derivative for 4. So we get 6 times 4 minus 6, which is positive 18, which is greater than 0. Thus, 4 minus 70 is a local minimum point. So we have a U shape and we'll have a minimum point. F of x equals x squared natural log x for x values elements of the real number set where x is greater than 0. Show that f of x has a local minimum at x equals 1 over root e and find this local minimum value. So let y equal f of x equal x squared ln x, which is x squared natural log x. So since these two are stuck together, which means multiply, we're going to use the product rule to differentiate. So the x squared is the u and the natural log x is the v. So we have u, which is x squared, multiplied by dv dx. So we differentiate the natural log of x and we get 1 over x, plus the v, which is the natural log of x, multiplied by du dx, the derivative of x squared, which is 2x. Multiplying, we get x plus 2x natural log x, and factorising, we get x times 1 plus 2 natural log x. So now we have our derivative, and what we do is we put it equal to 0. So we put dy dx equal to 0, so we put x times 1 plus 2 natural log x equal to 0. And then we divide both sides by x, so x divided by x just cancels, or goes once, and 0 divided by x is just 0. And then we change the 2 natural log x to 2 log base e x, which is the same thing. So we have 1 plus 2 log base e x equals 0. So we bring the 1 over the equal sign, it becomes minus 1, and then we divide by the 2 to get the log base e x on its own, and we end up with log base e x equals minus a half. Then we use our scorpion tail method, so we say e to the power of minus a half equals x. So x equals e to the power of minus a half. The minus gives us 1 over, gives us the reciprocal. And we have e to the power of positive a half as our denominator. And e to the power of a half is root e. So x is equal to 1 over root e, which is what we were asked to show. So now we need to find its local minimum value. So we know from the previous slide that dy dx, the derivative, is x times 1 plus 2 natural log x. So now we need to find the second derivative, so d squared y dx squared. So these two are stuck together, which means multiply, so we're going to use the product rule. So our x is the u, and the 1 plus 2 natural log x is the v. So we get x times 2 over x plus 1 plus 2 natural log x times 1. And that gives us 2 plus 1 plus 2 natural log x, which gives us 3 plus 2 natural log x. Now we know that x is equal to 1 over root e from the previous slide. So we swap this x for e to the power of minus a half, which is the same thing as this. So we have the second derivative, d squared y dx squared equals 3 plus 2 log base e, e to the power minus a half. Using our laws of logs, we can bring the power down in front of the 2. So minus a half multiplied by 2 is really minus 1. So this just becomes minus log base e. So we have 3 minus log base e equals 3 minus 1, because log base e, when the base and the argument are matching, we just get 1. So 3 minus 1 is 2, and 2 is greater than 0. Thus, y equals f of x has a local minimum at x equals 1 over root e. So it has a minimum point. So the local minimum value is the value of y at the local minimum point. So if x equals 1 over root e, then y equals 1 over root e squared log base e to the power of minus a half. So basically, if you take x squared natural log x and you swap each of these x's for 1 over root e with brackets. 1 over root e squared is really 1 squared, which is 1, over root e squared, which is root e times root e, which is just e. So you get 1 over e. And log base e to the power of minus a half, gives us minus a half. So if log base e to the power of minus a half equals x, we use our scorpion tail method. So base e to the power of x equals e to the power of minus a half. So we have e to the power of x equals e to the power of minus a half. The e's will cancel because we have the same base on either side. And we're left with x equals minus a half. So that's how this changes to be minus a half. And then multiplying, 1 multiplied by minus 1 is minus 1. And e times 2 is 2e. So we end up with 1 over 2e. So this is the local minimum value. This is the value of y at the local minimum point.